Professor Feiner. Thank you for your kind introduction. Hello, my name is Junhyub Lee, and I will be presenting Projective Windows, bringing Windows in space to the fingertip. I am the main author, and my co-authors are Sang-gyun An, Yongkwang Kim, and Seokhyung Bae. We are all from the Department of Industrial Design, KAIST, South Korea. Let me begin. So a couple of years ago, I was with a friend at a Starbucks talking about the future of technology, as we all do. But being the wise HCI researcher, I made a $100 bet that in 5 years, whenever you walk into a Starbucks, more than half of the people will be wearing some form of AR devices over their faces. And thanks to companies like HTC, Oculus, Microsoft, and even the mysterious Magic Leap, it seems increasingly likely that I'm going to get my $100. So come and find me at KAI 2020. So when this future arrives, we are going to see a massive change as the entire space around the user becomes an interactive computing medium. And when we talk about this new spatial medium of the future, we love to talk about immersive 3D contents, just like the hologram of Princess Leia in Star Wars. But I'm not going to talk about immersive 3D contents today, because I believe that the vast majority of contents that people consume through their AR devices will still be two-dimensional. Contents like texts, images, and videos will still be around for a long time, and we need a good way to interact with these 2D contents in 3D space. So what will 2D contents actually look like in my everyday life when I'm in augmented reality? To figure this out, I began to do a lot of thought experiments. For example, this is what I see when I wake up in the morning, like literally. When I put on my AR glasses, what will I see? Maybe there will be Facebook on the wall. Maybe Twitter on the left. Maybe there will be today's weather and temperature on the door of the wardrobe so that I know exactly what to wear. Okay, but what if I notice something interesting on Twitter? How do I interact with it? For instance, I would like to somehow reach out and bring it to my hand and also touch it like it's there. Continuing my thought experiment, this is what it looks like when I sit at my desk. There are two physical screens, but in my augmented reality, my workspace would not be limited to the screens, but include the entire space around them. For instance, I might have some virtual sticky notes and some animated family photos playing at the back. I might have a couple of web browsers sitting on the desk that I can refer to when I'm doing my main work on my computer. Quite often, I would like to somehow pick and move my side window to the center of my workspace. And at the same time, somehow make it bigger so that I can see it better, even from a distance. To summarize, through my thought experiments, I showed that the user should be able to bring even distant 3D windows instantly to the fingertip for interaction, put 3D windows anywhere, even at any distance, and easily move and scale them. Also, the user should not have to use hardware controllers or something like move and scale widgets for what is such a routine task in augmented reality. In designing a new interaction technique that satisfies these goals, I came across this really inspiring concept called image plane interaction, proposed by Pierce and colleagues. Using this technique, you can easily bring even distant objects. For instance, you can place your fingertip over a distant object and instantly bring that object to your fingertip. As you can see, this allows the user to easily bring objects that are far away. However, it does not support moving, scaling, and placing of windows. Now let me introduce you to our novel interaction technique called Projective Windows. The basic idea behind our interaction technique is very simple. In 3D space, when an object is far away, it appears small. It has a small apparent size. When the object is close, even though the absolute size is the same, it appears big. It has a large apparent size. So you can see in this video, even a very small object can appear as big as a considerably bigger object that is far behind it. The important thing here to remember here is that an object has two sizes, an absolute size and an apparent size. Now let me show you how Projective Windows works. Although the user might notice that there is some interesting news on a 3D window on a tea table nearby. Even though the window is out of the user's reach, the user can simply raise the hand, the user simply raises the hand and grabs the window. And when the window is grabbed, it is instantly brought to the user's fingertips, just as in the image plane interaction you just saw. Note that when it does, the absolute size of the window is reduced so that the apparent size of the window can remain the same. Once grabbed, the window's absolute size is fixed, so the user can bring the window closer to the eyes to make it appear bigger. Note that this time, the absolute size is constant, while the apparent size is changed. The user can also move it away from the eyes to make it appear smaller. The user can move it to a place where the user can see it better. So the user simply moves the hand while holding the window. When the user wants to make the window bigger, again, the user brings the window closer to the eyes. When the user releases the window, the absolute size is changed so as to maintain the same apparent size. In effect, the user projects the window onto the wall. So the small window that used to be sitting on the tea table is now a large TV-sized window hanging on the wall. The user can do all this movement and scaling with one simple flow of motion without any other hardware controller or UI widgets. This is Projective Windows. Projective Windows strategically uses the absolute and apparent sizes of a window to enable grabbing, moving, scaling, and releasing of the window in one continuous hand gesture. Now let me show you Projective Windows in action. We implemented Projective Windows using an Oculus Rift VR headset and a Leap Motion hand tracking sensor attached on the front of the VR headset. Now watch how easy Projective Windows is to use. To grab, move, scale, and release a window. It only takes one operation and about 4 seconds. Now let's compare this to a more conventional interaction involving ray casting and widgets. The user performs a similar move and scale operations on a Microsoft HoloLens. Notice that the user must first aim the cursor at the separate move and scale widgets, and this is not necessarily easy when the window is relatively small. Also, the hand movements are linearly mapped to the window's movements. It takes the user 5 actions and about 20 seconds. Let's see Projective Windows again, this time step by step. The user simply grabs a window at any distance, moves it away from the face to make it smaller, and releases it to a vertical surface. Let's see that one last time, because we can. Easy, right? This is what the future of augmented reality interface using Projective Windows might look like. With our technique, any horizontal and vertical surface becomes a virtual pinboard for inspiration. You can enlarge and shrink windows, distant and near, in one continuous motion to inspect them and use them as reference. When you need to work on a different device, simply grab the window and place it on the device. When you're studying hard for the exam, you're going to need all the help you can get. Wouldn't it be nice if you could place them anywhere you want? There can be some distractions, but you can quickly view them and throw them away. After a long day, nothing is more relaxing than a good movie at the comfort of your sofa. Videos can start playing when they're projected on a large vertical surface and stop playing when they are retrieved. With our technique, you can interact with windows of any size and distance without breaking a sweat. Next, we quantitatively and qualitatively evaluated Projective Windows against the baseline technique. Each of the 12 participants moved and scaled windows 420 times, while the task completion times and operations counts were measured. We wanted to compare Projective Windows performed with the hand as tracked with a hand tracking sensor against the conventional ray casting method using widgets. but unfortunately the hand tracking sensor was not accurate enough for rigorous performance evaluation, as it experienced frequent gesture recognition errors and tracking losses. So we implemented projective windows using a hardware VR controller, where the buttons are carefully mapped to resemble performing projective windows with the hand. So the ray casting baseline technique was compared quantitatively only with projective windows using a controller. While the projective windows with the hand was analyzed qualitatively. And this is what the experiment looked like. In this video, windows are moved and scaled from an initial position using a conventional hardware controller, ray casting, and dedicated move and scale widgets in the corners. After each task, the user puts the controller at the starting position visualized as a virtual sphere to reset the controller position. Next, the same tasks are performed using projective windows using a hardware controller. The user first searches for the initial window and the target, and uses projective windows to move and scale the window so that it matches those of the target. The user's hand position is visualized as a green sphere. Also, this is what it looks like to perform the move and scale tasks using projective windows with the hand. I found compelling results. Because the participants did not have to aim at different move and resize widgets, they were able to perform tasks significantly faster, 22% faster, through a significantly smaller number of operations, approximately 40% smaller. While these are the overall numbers, I performed in-depth statistical analyses for different factors, such as the linear and angular distances and the absolute and apparent size ratios between the initial window and the target. Also, we conducted and analyzed the 5-point Likert scale surveys and interviews using ANOVA and post-hoc analysis. While these results are more thoroughly reported in the paper, I would like to share some of the insights that we discovered. First, projective windows is easy to learn. All participants could proficiently use projective windows after only a few tries. Next, a number of participants mentioned that using projective windows feels like using a touchscreen in space, while using ray casting feels more like a spatial mouse cursor. We found that comparison very interesting, and we think that this speaks volumes as to the intuitiveness of our technique. Surprisingly, participants mentioned that using projective windows with a hardware controller is not very comfortable, because it required a lot more hand movement while carrying the weight of the controller. The performance benefits of projective windows was more pronounced for greater scaling operations, meaning that with projective windows, it is easier and quicker to make windows a lot bigger or a lot smaller. Participants mentioned that they would prefer projective windows for more casual and unplanned tasks, such as, which is exactly what moving and scaling 3D windows involves. And lastly, the apparent size is a really crucial factor when designing a spatial user interface. Before wrapping up, I would like to announce that we have a demo today starting at 6 p.m. at room 220 BC. Our demo number is D412. While I did my best to describe projective windows, many of you who have done work in AR and VR know how hard it is to convey what it really feels like. So I invite everyone who is interested to come and try our demo. This concludes my presentation. Thank you for your attention.
Hi. Is it okay for me to go? Yeah. Hi, Andy Wilson from Microsoft. All of your examples of a course presented monocular, right? So in AR and VR, we have stereo displays. And so for very large scaling operations, that object is really going to be moving in depth. And I was curious if you had any observations on how people felt that it was in the same place, that projected in the same place as it moved from one depth position into the other, And in fact, it's moving quite a bit, right? And so the change in disparity, particularly in moving something very large and far away to something that's small and very close, is going to be quite dramatic.
Thank you for the great question. So the question was, because we have stereopsis, when the window is grabbed, essentially the window flies towards the fingertip of the user instantaneously, and that can be quite a large distant jump, and the user can feel a discrepancy or a discontinuity in the visual perception of the window. And it is true that there is a jump. There is a jump because we do have stereopsis, but there is also a certain level of visual continuity, and we did not explore enough about maybe the animation that would make it more a smoother transition. But there is a jump, but the participants did not report any difficulty in using the projective windows, and I think the task itself is casual enough that such a discontinuity does not matter that much. Thank you.
Dong Yoon from University of British Columbia. Fantastic work. What about in a collaborative scenario? So the operator, in an egocentric view, the apparent window size is the same. But for the other people who are seeing the operator changing the size of the window, what would be the best way to visualize the operation of the window changing to give the best operational awareness about the operator's task manipulation to the other people who are watching one changing the size of the window?
So is the question, what if there are collaborators and they're all using projected windows? Is that?
So one of them is using.
Okay.
What if others are using the one who are using projected window?
Okay, so the work we did so far deals only with a single user, but I think projected windows for collaborators is a very interesting concept, and we intend to explore that further. But I don't think that will be that much of a problem. Maybe one user can project one window very largely on a distant wall so that everyone can see, and maybe everyone can share that view. Does that kind of answer your question, or did I kind of not?
That's fine, thanks.
Thank you. You can come and see me after this. Thank you.
Thank you for a great talk. It seems like core to your implementation of projective windows is the notion of sacrificing control over positioning and orientation in favor of a simple interface for scaling and just snapping to particular orientations and particular locations. Did you get feedback from your users or testers about this trade-off, this lack of control versus the more powerful, but to your point, requiring more operations raycasting approach?
Okay, so that's a great question. So the question was essentially positioning anything in space is a 6 degrees of freedom manipulation, and that can be quite complex. And by allowing the user to only be able to attach windows to existing surfaces like vertical walls or horizontal floors, we essentially eliminated 4 degrees of freedom and reduced it to 2 degrees of freedom, right? So, and for the task of scaling and moving windows, the task itself is casual enough that those sacrifices were a good trade-off. And I think the participants mentioned that in our survey that projected windows would be more suitable for casual and unplanned tasks. And I think that is what those participants were referring to. Thank you.
Thank you so much.